Okay, good morning. So in today's session, we are going to discuss some basics about chemical reaction. So let us proceed with the introduction. So chemical reactions are associated with the chemical change, right? So change is due to the reactions that take place between the chemicals or in the chemicals, right? So whenever a chemical change occurs, chemical reaction is said to take place. Chemical reactions are usually irreversible and a new product is formed. So, after this session, we will be able to classify and classify a chemical reaction as a combination of decomposition, single replacement, double replacement, oxidation, reduction uh, reactions. We will also be able to predict the products when given a set of reactants for a given chemical process, and we will be able to write molecular ionic and net ionic equations for a given chemical process. And so, first of all, uh, you can detect that a chemical reaction has taken place based upon these five signs that indicate that it has a chemical reaction has indeed taken place. So, change in color is also a sign of the chemical reaction, and emission of the gas is also a sign of chemical reaction. Change in the temperature is also a sign of chemical reaction, and change in state means from solid to liquid, liquid to gas, or from gas to liquid or liquid to solid. This change in state or so these signs will indicate that the chemical reaction has taken place. So we use the word chemical reaction. In chemical reaction, we use the word reaction equations, right? So equation means in between where equal to sign is present. Okay. The word equation describes chemical change using the name of reactants and products. So equal to or here with the arrow, the chemical equation is represented. Okay, so on one side of that arrow is going to be the reactants and on the other is going to be the products. So here in this example, we see that reactants are methane and oxygen, and reactants are going to be on the left hand side of the arrow, and on the right hand side of the arrow you can see the product. Methane and oxygen are reacting with each other and producing the products carbon dioxide and water. Okay, so CH4 is the formula for methane, and oxygen is O2. In molecular form, its formula is O2. Okay, so we have 2 moles of O2 and 1 mole of methane. So the products formed are carbon dioxide, that is CO2 plus 2H2O. So this is an example of a chemical reaction equation. The simplest form of description. So a chemical equation is the simplest form of description of a chemical reaction. In a shorter form is by writing it in the form of an equation. Okay, so it is the simplest and shorter form we can represent a chemical reaction using these equations. Okay, we can uh, represent a chemical reaction in very short form. So here in this example, magnesium plus oxygen are reacting and producing a product MgO, magnesium oxide. Here an arrow is missing in between, but you see the magnesium and oxygens are the reactants and MgO is the product. Okay, the reactants are written on the left side and the Product is written on the right side of what arrow, which is missing here. Not worry. Okay, here it should be the arrow. On the left side are going to be your products, and on the right side are going to be your, sorry, on the left side are going to be your reactants, and on the right side is going to be your product. An arrow is placed between them to show the direction of reaction. So what are the characteristics of a chemical equation? The equation must represent known facts. The equation must contain the correct formulas for reactants and products. The law of conservation of mass must be satisfied. So therefore, that is why, because of this third condition, we saw different numbers prior to a molecular formula in a chemical reaction because of the law of conservation of mass. And we can also show phases in the chemical reaction equation inside the brackets. So here S stands for solid, L stands for liquid, and G stands for gaseous. Although all three are is an example of water molecule. Okay, so molecular formula is the same, but still there is a chemical reaction going on because there is a change in the state of the matter. Here water is changing from solid then to liquid then to gas. Molecular formula is remaining the same, but state of the matter is changing. Then comes the balanced chemical equation. Balanced chemical equation means those equations that follow the third rule, that is the conservation of mass. The amount of mass that is on the left side must be on the right side, and the number of atoms must be the same on the left hand side and the right hand side. Okay, so this type of equation is known as balanced chemical equation. For example, you see here there are 2 moles of magnesium and 1 mole of oxygen molecule, or O2. Or we can say there is 2 mole of magnesium atom and there is 2 mole of oxygen atom. When we are talking about oxygen atom, then there is 2 mole of oxygen atom in this chemical reaction. So they are forming a product 2MgO. When the product you see there is 2 moles of magnesium as well as 2 moles of oxygen, as was the case in the react reactant side on the left hand side. On the left hand side you also got 2 moles of both magnesium atom and oxygen atom, and on the right hand side the number of moles is the same for each element, where both sides have 2 atoms of so here they are taking atoms instead of moles, where both sides have 2 atoms of magnesium and 2 atoms of oxygen. So this is an, on the left hand side there is an unbalanced equation, and on the right hand side there is balanced equation. So on the left hand side in the reactants you see 2 atoms of chlorine and 2 atoms of hydrogen, but on the right hand side of this fulcrum you see only 1 atom of the hydrogen and 1 atom of chlorine. So the number of atoms in on the reactant side, number of atom on the product side are different. So it is an unbalanced equation. Whereas on the right hand side there the number of atoms of each element are the same on both the sides. So it is an example of balanced equation. Then there is then there is this example of CH4 plus 2O2. What is CH4? Methane plus oxygen. Okay, so it is giving us the product carbon dioxide plus water. So here you also see how many atoms of carbon are there in the left hand side. Only 1 atom. Hydrogen has 4 atoms and oxygen has also 4 atoms. So on the right hand side it also must be the same. So carbon on the product side is also having 1 atom, oxygen's 2 here and 2 here. So 4, which is equal to the number of atoms of oxygen on the left hand side, and the number of atoms of hydrogen atom on the right hand side is 4. 2 into 2, 4, similar to the number of hydrogen atom on the left hand side. Okay, so one carbon atom on reactant side as well as the product side. 4 hydrogen atom on the reactant side as well as on the product side, and 4 oxygen atom on the reactant side as well as on the product side. So here you see there are 2 moles of sodium, and again there are 2 moles of chlorine atom. But when we're talking about chlorine molecule, then there is 1 mole of chlorine molecule. Okay, so here 2 moles of sodium and 1 mole of chlorine atom. Sorry, 1 mole of chlorine molecule. Okay, so when they react, they are forming 2 NaCl. Here they got 2 moles of both sodium as well as chlorine. Okay, so suppose if we are taking here 10 mole of sodium and 5 mole of chlorine, then the product is having 10 mole of NaCl, right? 10 mole of chlorine as well as 10 mole of sodium, because on the left hand side we also got 10 mole of sodium as well as 10 mole of chlorine atom, not chlorine molecule, because when we are talking about chlorine molecule, then we have only 5 more. Okay, so number of moles are going to be same in both the sides of a chemical reaction equation. Now there are different types of chemical reactions. One is combination reaction. Here two elements react and combine to form a product or a molecule containing both the elements in the reactant side. Then comes your decomposition reaction. Eh, Now this reaction results in the splitting of a compound to its constituent element. Okay, so in this example, AB is the compound or a molecule, and it is being split into constituent A and B element. Then third type of chemical reaction is single displacement reaction. So here, as you can see from the example, uh, A plus B C. So here A is replacing B or displacing B, and is producing a new product, that is AC, and B is being released from the compound or from the molecule. Okay, so this is an example of single displacement reaction. Then comes the double displacement reaction. So here both the product, sorry, both the reactants that are reacting with each other are a compound of two elements. A, the first compound is AB and the second is CD. So in the result, A is replacing C from the CD, and B is replacing D from the CD. So C's place is taken by A and D place is taken by B. So there are two displacement going in the same reaction. So that is why it is known as double displacement reaction. Then the fifth type of reaction is redox reaction. It stands for reduction and oxidation reaction. When a element or when a molecule gain an oxygen atom in a reaction, then it is said to be oxidized. And when it loses oxygen atom, then it is said to be reduced. Let us see with other examples these different types of reactions. The first one is your combination reactions. So these types of reaction occur when two reactants combine to form one or more products. Calcium oxide plus water. Okay, it is giving you calcium hydroxide, CaOH2. Again, remember to balance the equation. So Ca is 1 on the left hand side, it is also 1 on the right hand side. Oxygens are 2 and hydrogen are also 2 on the left hand side, and so is on the right hand side. And second example is carbon plus oxygen molecule. So it is giving you carbon dioxide. It is a balanced equation because number of atoms of each element in the left hand side is equal to the number of atom in right hand side for each element. And these combination reactions are generally exothermic reaction, means uh, ap- they emit heat or they produces heat when the reactions is when the reaction is going on. Okay, which involve evolution of it during the reaction. So combination reaction, uh, here in this example, 2 moles of or 2 atoms of, either you can take it a mole or you can take it as atom, that is your choice. So there are 2 atoms of sodium plus 1 molecule of chlorine, but 2 atoms of chlorine, right? It is giving you NaCl, your common salt, having 2 molecules of NaCl. Okay, so number of atoms are the same on the left and on the right hand side. So it is an example of balanced equation. It is an example of combination reaction. Two elements, separate elements, are combining to form a product containing both the elements. Then come decomposition reaction. It is the reverse of combination. In the combination, two separate elements were joining to form a product having both the elements. Now in this example, a compound or a molecule will be splitting into its constituent molecules or atoms. So the type of reactions in which a single reactant breaks down to give simpler products are called decomposition reaction. For example, here you see 2 moles of water, it is splitting or decomposing to give products 2H2 or 2 um, molecules of hydrogen plus O2, 1 molecule of oxygen molecule. Okay. So when a decomposition reaction is carried out by heating, it is known as thermal decomposition. So this example shows you how decomposition reaction takes place. So 2H2O, 2 molecules of water. So here you can see in the picture H is representing hydrogen and O is representing oxygen. And after decomposition, they are splitting to produce 2 molecules of H2 and 1 molecule of oxygen, that is O2. These are all examples of decomposition reaction. Hydrogen peroxide, what hydrogen peroxide is being split to produce water and oxygen. Then electrolysis of water. So 2 molecules of water electricity is being passed through the water and it is splitting into 2 molecules of hydrogen as well as 1 molecule of oxygen. Then nitrogen triiodide. So 2 molecules of nitrogen triiodide is split into nitrogen molecule N2 and iodine, 3 molecules of iodine molecule. So on the right hand side there are 6 number of iodine atoms and on the left hand side it is the same. Similarly, there are 2 atoms on the left hand side of the nitrogen and it is the same on the right hand side. The general form of your decomposition reaction is AB Okay, and AB as a reactant, and it is producing A and B, so it is splitting its constituent. Then comes the displacement reaction. So in these types of reaction, a particular element in the uh, in the reactant side is replacing a another element in a compound. Okay, so the reaction in which a more reactive element displaces a less reactive element from its solution is known as displacement reaction. They are of two types: single displacement reaction and double displacement reaction. So in these pictures, there are both example of both single replacement reaction and double replacement reaction. In single replacement reaction, you see magnesium plus copper sulfate. So they are reacting, and magnesium is replacing the copper. Why? Because magnesium is more reactive than the copper, so it is replacing the copper and taking its place and forming a new substance or a new compound, that is magnesium sulfate, and releasing the copper in the process. So general form is A plus PC, that will result in AC plus B. Now in double replacement reaction, you see here our reactants are calcium carbonate plus 2HCl. Okay, two molecules of HCl. So they are reacting, and calcium is replacing your hydrogen here, right? And hydrogen is replacing your calcium. Okay, so they are both are replacing one another. Calcium is replacing hydrogen, so calcium is taking the place of hydrogen, and hydrogen is placing uh, taking the place of calcium. They are forming new compounds: calcium chloride 2 plus H2CO3. So why they are replacing? Because uh, chlorine must have more affinity towards calcium, whereas carbonate must have more affinity towards hydrogen. So that is why they are replacing one another. So the general form is AB plus CD. A is replacing C, or A is taking the place of C, and C is taking the place of A. So these are example of a single displacement reaction. We have got lead chloride, that is PbCl, plus potassium iodide, that is Kl. Okay, so PbCl2 plus Kl, when they are reacting, Pb is replacing your K, so it is becoming KCl plus, and K is replacing your Pb, so it is becoming PbI2. Similarly, this example goes, in this series you can see the elements in the order of their reactiveness. So the most reactive elements are on the top of this chart, and as we move down the chart, the reactivity is decreasing. So at the bottom you will find least reactive element, and at the top of this list you will find the most reactive element among these. Potassium is more reactive than sodium, which is more reactive than the calcium, which is more reactive than the magnesium. Then comes your aluminium, then comes your carbon, then comes your zinc, then comes your iron, tin, then lead, then hydrogen, then copper, then silver, and platinum is the least reactive of them all in this uh, list. Okay, now comes the next redox reaction, very important reaction. So if a substance gains oxygen during a reaction, it is said to be oxidized. If a substance loses oxygen during a reaction, it is said to be reduced. Reactions in which this type of change occurs is known as oxidation and reduction reaction, or redox reactions. For example, you can see the reactants are copper oxide and H2. So here oxygen is copper is losing the oxygen and hydrogen molecule is gaining the oxygen. So copper is being reduced. There is a reduction going on with the copper, and whereas hydrogen molecule is being oxidized. Redox reaction. We will proceed with uh, representing ionic reactions as a chemical equation. How to write the equations? So for reactions that involve ions dissolved in water, there are several different ways to express the overall process as a chemical equation. For example, the overall molecular equation shows all ionic components as neutral components, but the ones that are dissolved in water are denoted with this symbol AQ in the bracket denoting aqueous, okay, in the quotation mark here. Note that the ionic substances do not exist as molecules, but we write them out as though they were, right? In the following example, two water-soluble compounds trade partners to produce one dissolved ionic compound and one solid precipitate. So precipitate is when uh, two chemicals react. So the ones that get dissolved get separated and they exist as ions. They exist as ion in the dissolved form. But the ones that precipitate, they do not dissolve and they get precipitated to the surface of the beaker. Right? So we can represent the reactions like this. A B is a compound and it is aqueous, means it is getting dissolved. AB, it is getting dissolved, and another compound is CD. It is also getting dissolved in water, means it is existing as ionic form, not in molecular form. And when they react, so here they are. It is an example of double substitution. So here A is substituting C and uh, B is substituting D. Right. So we have got two new compounds. AD, again it is aqueous, means this new compound is in dissolved form, in ionic form in the solution, and another compound or another chemical that is being formed as a product of the reaction is CB, and it is in the solid form, means it is it is being precipitated to the bottom of the beaker. Okay, it is not in the dissolved state. So in reality, the aqueous substances do not exist as molecules or ion crystal lattices. Instead, the individual ions are dissolved and distributed throughout the solution. If the reactions above were written as an ionic equation, it would look something like the following. So, as you know, A and B and both C and D are denoted here with the aqueous denotation. Okay, because they are not in their molecular state, they are dissolved and they exist as ions. So they can be written separately. So A positive, so it is a cation, and because it is dissolved, it is accompanied with the aqueous, and B is an ion here, so it is also separated from A plus at the moment in the aqueous condition. Then and C cation and D anion. These are also not in the molecular form attached to each other, but these are also dissolved in the solution, aqueous solution. But when they are reacting, uh, A and D are they are forming new compound A and D. This is still an in the dissolved state. So it is being denoted with the aqueous sign. But the new compound that another new compound or another new product that is being formed here is Cb, and it is not dissolved. It is being precipitated and collecting at the bottom of the beaker. Okay, so this is how you can write the ionic reaction as the chemical equation. Okay, in this example, the various reactions components are presented in a form that is closer to the way they actually exist during the reaction. The aqueous components are separated into ions, and the precipitate is found as a combined solid. We are assuming in this example that A and C form cations with a charge of A plus 1, while B and D form anion with a charge A minus 1. But in real life, we have to see their position in the periodic table, that whether that particular atom or that particular element is going to become a cation or an ion depending upon their valency. But in this case, we are assuming that A and C are cations and B and D are anions. Now notice that in the ionic equation, A plus and D minus were unchanged over the course of the reaction. They exist as aqueous ions on both the reactant and the product side. So before the reaction, they were A positive and D negative as separate entities, separate ions dissolved in the water, and after the reaction, they still exist as separate entities dissolved in water, separate from each other. I mean, okay. So we can cancel out those, and we can only represent those that are changing their form. Okay. In other words, these species did not experience any net change. These were positive and they did not experience any net change because they are same before the reaction and after the reaction. Ions that are present in solutions but do not participate in the overall reactions are known as spectator ions. So A and D are spectator ions. The ionic equations can be simplified to the net ionic equation by cancelling out all the spectator ions. So we can cancel out A positive and D negative in both the sides, in both the reactant side and product side. And the net ionic equation will become B negative in aqueous state and C negative in aqueous state, sorry, C positive in aqueous state prior to the reaction, and after the reaction they are forming a new compound Cv having a solid state. Now let's look at these three types of equations again using a real example. So if we were to mix aqueous solutions of the potassium iodide and lead nitrite, lead iodide would precipitate as a solid and potassium nitrate would remain dissolved. This can be represented by any of the three following equations. So first one is the molecular equation 2Ki, that is potassium iodide in the aqueous state means in dissolved state in the ionic state, plus potassium, sorry, plus lead nitrate, and it is also in aqueous form or in dissolved form. When they are reacting, they are producing new compounds like KNO3, that is potassium nitrate in the aqueous uh, state, that is in the dissolved state, and another product that is lead iodide, that is the precipitated or the solid product. Then we can write it in the ionic equation form like 2K plus and 2I minus plus lead 2 plus in the aqueous state and 2 nitrate ion in the aqueous state. And of course, after the reactions, Your potassium and nitrate are still in their aqueous or dissolved state. These are spectator ions, and lead and iodines are combining and forming a new solid compound that is precipitating to the surface of the beaker. Now, the third representation can be net ionic equation. From this equation, we can remove the spectator ions, and only the ions that are changing or that are participating in the reaction will be present in the net ionic equation. Okay, so lead 2 plus cation in the aqueous state plus 2 iodine ion in the aqueous state. They are reacting and forming a new compound, that is lead iodide in the solid state. So these are the three types of uh, representation of your ionic reaction. These are three represent equation representation of your ionic reaction. We can also predict solubility of ionic compounds uh, in very general sense, not very accurate, but in general sense, we can predict solubility of ionic compounds. So, how do we determine which ions are likely to form an insoluble precipitate and which will remain dissolved in water? So, by combining various ionic solutions, chemists have come up with some general guidelines for whether a given cation anion pairing is likely to be soluble or insoluble in water. Means either they are going to remain in aqueous state or dissolved state, or they're going to uh, combine and form a solid state and precipitate in the process. It should be noted that such an approach is an oversimplification that I have already said, that we can predict solution in a very simplified way. Each compound has its own solubility value. So two soluble compounds might have very different abilities to dissolve in water. And additionally, even insoluble salts can dissolve in water to a very limited extent. So we will take a more quantitative approach to solubility in chapter on solutions when we will discuss that. However, qualitative rules like the ones in the following table are useful for predicting whether a precipitate is likely to form when combining moderate amounts of specific cation and anion. So you can see the table having three columns: type of particles, soluble and insoluble. So for common cations like your alkali metals that are in the first group of a periodic table, like lithium ion, sodium ion, potassium ion, okay, or the NH positive cation. These are soluble. These are soluble means these ion will remain dissolved even after the reaction. Then comes your common anion, that is ClO4 negative and NO3 negative, nitrate and chloride. So they will also remain dissolved. So they will not get precipitated after the reaction. They will also remain in their aqueous or dissolved state. Then comes the halide. Halides are 17th group and are most reactive group in the whole of the periodic table. So most fluorine, uh, bromine and iodine anions compounds, they will also remain soluble or in the dissolved state. But some of the compounds that include Ag, lead, your silver, lead, and this Hg2 positive cation, they can form compound and precipitate and hence become insoluble after the reaction. Okay. Then comes your sulfate. Most SO4 2 negative compound. Most of your sulfate compounds will be soluble, means they will be in dissolved state. But some compounds like uh, lead sulfate, silver sulfate, or Hg2 sulfate, calcium sulfate, SrSO4, and beryllium sulfate, they will these compounds will precipitate after the reaction and solidify. Then comes your sulfide. S sulfide is S2 negative anion. So compounds with NH4 positive or a metal from group 1A and 2A as cations. Okay, what is 1 and 2A group? It is alkali metal and alkaline earth metals. Okay, the sulfide of these group will remain soluble. But other than that, most of your sulfide compounds will become insoluble and precipitate to the bottom of the beaker. And your hydroxide, your OH negative group, compounds with NH4 positive, Ba2 positive, or a metal from group 1A as cation. Metal from 1A means alkali metal. So compound of hydroxide with alkali metal, they will dissolve. They will remain dissolved state. But most of the other compound of OH negative anion will get solidified and precipitate and become insoluble in the process. Then comes your carbonate, phosphates, and sulfide compounds with NH4 positive or a metal from group 1A as a cation. Again, 1A, you must remember 1A is alkali metal, lithium, sodium, potassium. Compounds of NH4 or metal from group 1A as cations. Compound of carbonates, phosphates, and sulfides with these uh, groups, this 1A group and NH4 positive, will remain soluble in the ionic state. But most of the carbonate compounds, other than the mentioned in the soluble column, other than that, most of the carbonate compound and CO4 3 negative phosphates and SO3 2 negative, that is the sulfide compound, they will solidify and precipitate to the bottom. So this gives you a general idea or oversimplification of which uh, compounds will solidify and precipitate and which will remain in the dissolved form. Okay, then comes your combustion. So combustion occurs when a hydrocarbon reacts in the presence of oxygen to produce water and carbon dioxide. These reactions are very exothermic, means they emit a large amount of energy. It means that they produce large amounts of heat. Combustion reactions are quite common in our everyday lives, such as the burning of gasoline to fuel a car. The chemical equation for combustion reaction has the following generic form. So CXHY, this is, as you know, is the formula for your methane, ethane, propanol, ethanol, etc. Okay, this is the formula for your organic compound containing both carbon and hydrogen. So general form of the formula, general form of the equation will be CXHY plus O2, means they will react with the oxygen. That is what combustion is, and they will produce water H2O and carbon dioxide. So the process of cellular respiration can be thought of as highly controlled version of combustion reaction. Okay, so we do not literally burn hydrocarbons in our body, but the overall reactions and products are the same. Hydrocarbons such as sucrose, okay, are combined with oxygen in a series of enzymatic steps to produce water, carbon dioxide, and energy, which is stored in the form of reactive molecules. The unbalanced chemical equations for this overall process is shown below. So this is sucrose plus oxygen, and it will, as mentioned earlier, will produce carbon dioxide and water. But this is unbalanced. We are not representing, or we are not here stating how many moles of which molecules are in the reaction. side, in the reactant side or in the product side. So what was the summary of the lesson? Combination reactions occur when two or more reactants combine to produce a single compound, and decomposition is the reverse. Single replacement reactions occur when one reactant replaces part of another compound to form a new substance. And a common type of double replacement reaction occurs when two ionic reactants exchange anions, making two new ionic compounds. The precipitation of solid is common result for this type of reaction. The combustion reaction involves the reaction of hydrocarbon with that of oxygen, and as a result producing carbon dioxide and water. This is the summary of the result. Sorry, summary of the lesson.